So Math 105 written assignment is to find a set of data values, a graph or a table that looks linear or looks exponential. The linear is pretty straightforward. You just have to pick a couple of the points that you think will make a line that flows through the points. And then finding the slope is the harder part, and that's demonstrated in example 1 in the book and example 2 in the book on how to calculate that slope. So check those out. Exponential is a little bit harder, so let's try that one. So here I have a graph from usafacts.org, which is a reputable source, and this looks exponential to me. It starts off slow, shallow, and then gets steeper. And this is the total federal, state, local government debt. And you might know in Congress right now, they're arguing over whether to raise the debt ceiling because we are about to reach it and we need to pay our debts. So the numbers here, again, are pretty big. We can see down in the early 80s, it's a little over $1 trillion. And then in the 2000s here, it's 22, 23, $20 trillion. So I can either grab some of these numbers by just, pointing here and grab the number for 85 and 1980 and 1990 and 95. I don't need all of them. I just need some of them. Sometimes the site you find the data at will also have a place that you can download that. And this one has a see the table here. So I can grab a table of the values too. So I copied that table, stuck it in my spreadsheet in a couple of different ways. So here's the full data set here in the first two columns. And what I need to do is estimate the growth rate or the growth multiplier. And this column is me trying to estimate that. So I want to explain how I did that. Button, there we go. So we know our recursive model for exponential growth that we have some future population or amount is the growth multiplier times whatever the previous amount was. Now, if we just divide that previous amount to the other side, then that means the ratio of two consecutive years, in this case, should give me the growth multiplier, that 1 plus r. So in my spreadsheet, I just asked my spreadsheet to divide the 1981 amount divided by the 1980 amount, and then I just filled that down. So calculate that one and fill it down, and I can see there's slightly different growth rates for each pair of years, and it ranges from around 2% to maybe 15% increase, and sometimes there was a decrease, the debt went down. So then what I said, all right, well, since they vary quite a bit, let's average them. So here I just calculated the average of all those growth rates year by year. And on average, the growth rate of the US debt from 1980 till 2022 increased by about 8.4% per year is what that tells me. So my growth multiplier is about 1.84. So then I just grab the data for every 5 years to look at a graph of it. So the blue points are every 5 years until the last two. I decided to put 21 and 22 in there also. And so you can see, they rise up kind of like an exponential function to here. And then I calculated my model next to it. How did I do that? Well, I just typed my explicit model, which would be starting with the amount in 1980, 0.93, multiply by my growth multiplier, 1.084, and raise that to the power how many years went by. Well, to figure out how many years went by, I have to count the number of years after 1980. So that would be parentheses, whatever the current year is, minus 1980. And then I just fill that formula down, and that's what you see here. So summary of what I have so far. Is my average growth multiplier for this situation was about 1.084. So that tells me that my explicit model, for P, which is going to be the US debt in trillions of dollars, and N is years after 1980. We're going to know what the variables mean. would be Pn equals the 1980 amount, 0.93 trillion, times my 1.084 raised to the power n, which is years after 1980. In my spreadsheet, I had to subtract to figure that out. Sometimes we make another column for that. So then what I did is, well, let's make a prediction for a future amount like 2005. So in 2025, sorry. In 2025, n, 2025 minus 1980, that's 45 years later. So on my spreadsheet, I would calculate, or on my calculator, what's 0.93 times 1.084, the power 45. And I have that already calculated here. It comes out to be, let's see, I used a slightly different number there. Let's double check. Let's fill this down. 35 trillion, holy moly. So to plot that as a point, I just type 35 over there. And this point right here is not from the original data. That's just my prediction. Right, so it's not part of the original data there. That was my calculation. Okay, so if your data does go year by year, you can just divide consecutive years. Right, take the current year, divide by the previous year's amount, and check a whole bunch of them to try and find an average. What if it's not every year? What if it's like every 5 years? Then it's a little bit more complicated. So let's try that over here. So here I have data, same data, but it jumps every 5 years. And so I'm going to do kind of the same idea. I'm going to take the current amount here, divide by the previous amount, and it gives me a multiplier, sure, let's fill down, of 1.92, 1.58. Now that is a 5-year multiplier, not a 1-year multiplier, which is a bit more complicated. So a 5-year multiplier means that you basically have a 5th power floating in there. So it's like having the 1.084 to the 5th power. How does one undo a 5th power? Well, it turns out to undo a 5th power, raise it to the 1/5 power, because a power to a power multiplies. 5 times 1/5 would give you 1.084 to the first power, which is just 1.084. So that's what I need to do for those numbers. I need to undo that 5th power. So what I'm going to do is I'm going to do that after I average them. So here I'm going to average them. Again, I mentioned exponential models are a little bit more complicated than reality because finding that multiplier or percent increase or decrease is a little trickier. All right, so that's the average of those numbers there. So the next thing I want to do is I want to take that number there and raise it to the power parentheses 1/5 to undo the 5 accumulated years of multiplication of growth. And to two decimal places there, it gives me, and those aren't dollar amounts, by the way. That's a mistake. Let's get rid of the dollars. They're just numbers. And let's show another decimal point or two. Yeah, so if we skip all the years in between and just look every 5 years, average them and undo that 5-year multiplication, we get a growth rate of about 0.87. Seems a little high to me, but might work. So what if we change this from a 0.84 to a 0.87 and fill that down? I think my red line might be a little higher than the blue one, blue points. Yeah, it fits pretty good in the beginning here, but then later it doesn't do such a good job. And you don't have to stick with what the average was. You can just play around and guess. So here I had a guess of 0.84 for the growth rate. I tried 0.87. The 0.84 seemed a little steep to me too, so maybe 0.83, I don't know. Is there a best way to do this? If you take a statistics class, you'll learn a better way, usually in the second quarter of statistics. So I'm going to try a 0.83 growth rate. Fill that down. That gives me about 33.6. for my estimate for 2025. And that's a little better given the last 3 years, 20, 21, and 22. I feel a little more comfortable with that one right there. So, fun and games with exponential growth models. Good luck, have fun. Catch you later.